7 from 1D kinematics last time. Does anyone have any questions about any of those? All right, so just as a reminder, we're working on 1D kinematics of particles. And the meanings of 1D and kinematics and particles are the kind of thing that I like to put on the lecture quizzes. We'll probably have our first one next week. I'll tell you for sure closer to it. But that's the kind of thing that you want to notice as you read through your notes. And we've done a couple example problems with 1D kinematics of particles. We did a car stopping, and we did a ball rolling down a ramp. But the most important type of problem that has constant acceleration is projectile motion and free fall problems. So that's what we're going to talk about today. And the weird thing that I'm going to tell you is that if there was no air resistance, so air, is always sort of fighting against things that are trying to move. Usually I shouldn't say usually, but in a lot of cases, it doesn't make that big a difference in the motion of objects. In some cases, it makes a big difference. But if you got rid of all that air resistance, any two objects, no matter what their weights were, would fall the same way with the same acceleration downwards due to gravity. That's a hard thing to wrap your mind around, and I'm going to try to, talk about that a little bit to try to get you to. So probably, I think everybody's intuition is kind of that like heavier things tend to fall faster because of gravity, and you got to kind of undo that intuition because it's wrong. And so the first thing that I want to do is show a video where, because that sounds pretty theoretical, like how do you know whether, what happens if there's no air resistance? Well, you can get rid of air resistance completely if you pump all the air out of something. That's pretty tedious to do in any container that's bigger than something really small, But the video I'm going to show you is a building that they use for aerospace testing, where it's this giant building where they can actually suck all the air out of the building. And before they suck the air out of the building, they're going to drop a feather and a bowling ball at the same time. And it's going to do exactly what you expect. The bowling ball is going to smash down to the ground. The feather is going to flutter down slowly. But then they're going to, suck all the air out of the building, which takes them a lot of time. And then they're going to show us the same drop again. And what you're going to see is kind of amazing. I mean, we're not used to seeing stuff like this. The feather and the bowling ball are both going to fall at exactly the same rate, hit the ground at the same speed. The feather's going to bounce off the ground violently, So let's watch it. Right now, can you tell whether the air is in or out of this building? Yes, because he's alive. That's correct. So they're going to make sure he gets out of there before they suck the air out of it. I wish they showed it at real speed, but they only show it in slow motion. Isn't that cool? Okay. So, um, that is one of a small number of common misconceptions that I just want to be, explicit about. Um, so, this is common misconception number one, and you have to kind of retrain your brain um, to accept this. Um, so, it's often believed that gravity makes heavier objects fall faster. And that doesn't put you in bad company to think that it seems like that's true. Some of the great scientists and philosophers in history, in ancient Greece and stuff, still believed that this was true. But actually, what happens is gravity makes all objects fall with the same acceleration, when heavier objects do fall faster, like you saw at the beginning of the video where they dropped the bowling ball and the feathers, and there was a huge difference in how fast they fell. So when heavier objects do fall faster, it's just because of air resistance. Okay, so in a vacuum, any two objects that aren't touching the surroundings would fall the exact same way, including a helicopter. You know, the reason a helicopter can fly is because its rotors have a reaction with the air. The reason an airplane can fly, same thing. So anything that's not touching the surroundings without air resistance would fall downwards with the same acceleration. And if you ignore air resistance, if you ignore air resistance, all objects that are free of the surroundings accelerate at 9.81 meters per second squared down. So this is what we're going to use all the time as the acceleration. Okay. So in order to make sense out of this, you kind of have to have a sense of when air resistance is going to affect the motion of an object a lot and when it isn't. So let's just go through a list of the things that affect, that determine the effect of air resistance on an object's motion. So what determines the air resistance effect on an object's motion? The first one is the object's mass. So the air resistance doesn't increase when an object is lighter, but the gravity force decreases when an object is lighter. So in the sort of tug of war between those two things, all things being equal, lighter objects' motion is affected more by air resistance. So if everything else is the same, all else equal, lighter objects have their motion affected more by air resistance. Okay, so like an example of this would be, imagine a ping pong ball and a pinball. So one of them's solid metal and one of them's hollow, very light plastic. They're basically the same size, right? So everything else is the same except the masses of the two. And if you drop both of those two things at the same time off of the roof of a building, the pinball would hit the ground a lot sooner than the ping pong ball, because air resistance would affect the fall of the ping pong ball more. Okay. Are you with me on that? Any questions about that? So I'm going to just put that here. This is what would happen if you drop a pinball versus a ping pong ball. The second thing that affects air resistance, that determines how air resistance affects the motion, is surface area. So if everything else is the same, all else equal, an object with more surface area is going to be affected more by air resistance. So some things that that have yes.
Question, like, if in that building, like, just for the idea, like, if birds would be able to breathe, how would that affect their flying? Like, I was just thinking about. Like,
Yeah, nothing could fly. Nothing would be able to fly in any way. No, like there'd be no frisbees or helicopters or airplanes or birds. Nothing would be able to fly. Those all just have to do with the air reaction. Yep.
Would we be able to walk, like, if we could breathe, like, of course, like,
Yeah, we could.
Or would you like feel like you're like falling from the floor?
No, so right now we're really just thinking about stuff that's not touching the surroundings at all. We'd be able to walk fine because it doesn't affect, the ground would still be pushing up on us. We'd still have friction between our feet and the ground. So yeah, walking wouldn't really be affected at all, except like you said, you need to be able to breathe. And also, and also, when you take, so the other effect is when you suck the air out of that room, you know, the atmosphere has actually a very high pressure all the time. We're used to it, so we don't notice it. And it's acting on both sides of everything. So we don't notice that we're having to fight against a big pressure to put our arms up, because there's also a big pressure pushing up on our arms at the same time. But when you suck the air out, all of that pressure goes away. That's all just air pressure, you know? And so if you went from, this is kind of gross, but if you went from atmospheric pressure into that chamber, you would explode. I mean, everything, all the liquids in your body would instantly boil. You'd just be gone. There are, there's like really super high tech deep diving that people do, called saturation diving, where they live in a high pressure environment for like a month so they can, and in the early days of saturation diving, so what they do is they pressurize the place where they're going to live to the pressure of way, way down in the water. And then the people live in this pressurized tube for a month. And it would be really a pain for them to eat and everything else if that pressurized tube stayed at the bottom of the ocean. So every day when they're done with their work, they get pulled up in the pressurized tube up to the ship. So they're living on a ship at regular atmospheric pressure in a tube that's at the pressure of 150 meters below the ocean. Okay, so that's super weird, right? But in the early days, before they'd really fine-tuned all the safety protocols and stuff, there were a small number of accidents where people didn't open the, so you have to do all these pairs of hatches and then repressurize things. And there were accidents where somebody opened something without having the safety valve closed, and the pressure instantly went from the pressure at 150 meters below the sea to atmospheric pressure. And the way they describe it is there really were not bodies, particularly when the people died. Just everything turned to goo. All the blood boiled. There's like droplets of goo everywhere. And that's all that's left of the people. Okay, that's super gross, but it's pretty interesting. So anyways, I'm just saying, even if you have an oxygen tank on, don't go into a zero pressure environment from atmospheric pressure. Okay, you can find more about saturation diving at your local library. Also, these people, it's the most dangerous job in the world, saturation diving. They make it pretty safe now. But hydrogen has a narcotic effect when you get to a high pressure. And so, what did I say? Nitrogen is the problem. And so most of the air is nitrogen. But they can't use nitrogen in the air that these people breathe, so they replace it with helium. So these like super high risk, like macho guys living in the most dangerous environment in the world walk around sounding like Mickey Mouse all the time because all they breathe is helium. That's sort of a funny little, Okay, what am I talking about? So if everything else was equal, objects with more surface area would be affected more by air resistance. So that's what you see with feathers, parachutes. Feathers and parachutes are kind of optimized to have a huge amount of surface area that can catch the wind. And that's why there's very high air resistance effect for feathers and parachutes. Parachutes are designed to have as much air resistance as possible. And then the last thing that determines the effect of air resistance is the object's speed. And this one is extra important. This has a bigger effect than the other ones. And the reason it's extra important mathematically is that the speed is squared in the formula that determines air resistance. So small changes in speed have a big effect on air resistance. So all else equal, fast objects are affected more by air resistance than slow objects. And you're used to this idea just from riding a bicycle or whatever. Like if you're riding your bike at a leisurely pace, you don't notice much wind. But if you're riding as fast as you can, even though it's not tremendously much faster than when you're riding easily, you feel a ton of wind. You can hear it going by your ears. And the effect is a lot more air resistance. And so like if you want to ask yourself something like, how much does air resistance affect the flight of a baseball? Well, it's really important how fast the baseball is going to answer that question. If you take a baseball from this high off the table and drop it, air resistance has virtually no effect on it. But if you hit a baseball 500, like a baseball that's going to be hit for a home run in the major leagues needs to leave the bat at over 100 miles an hour, then there's a huge effect of air resistance on that baseball. Okay, so we're about to be able to use the constant acceleration equations to do projectile motion and free fall problems. There's two important facts that we're going to use in these kind of problems very often. So here are two useful facts. For 1D free fall and projectile motion problems. And what I mean by free fall or projectile motion problems is there's kind of two requirements. The first one is that nothing is touching the object. And air resistance is negligible. So if you're ever confused about whether to use free fall projectile motion approach for something, just ask yourself those two things. Can I ignore air resistance in the motion, and is anything touching it? But here's the two useful facts. The first one is if an object is dropped, then its starting velocity is the same as what it's dropped from. So if you're dropping an object out of the car window when the car is going 60 miles an hour, at the instant you let go of it, that object is moving horizontally at 60 miles an hour. Very quickly, it'll be moving very differently from that. But if all you're doing is just letting go of something and let it go, at that instant you let go, the velocity is the same as the vehicle or whatever that you're letting it go from. Okay. And the second one is if an object is launched up, then you know it's going to reach a highest point at some point before it starts coming back down. And at the highest point in its flight, the velocity is equal to 0. And we're going to use these facts a lot. So if you shoot something up into the air, it starts out with a high-ish velocity, and then it slows down until it reaches 0. And for just that one instant, it has no velocity, it's at rest. And then it starts to speed up back down. Okay. So let's just start doing some example problems. I'll do a couple and then I'll give some to you to work on. And we're going to use the exact same approach we did in the other 1D kinematics of particles, constant acceleration problems. So let's say that there's a bridge some distance above the water. And you want to know how high this bridge is, but you don't have a tape measure long enough. But you have like a rock or something. So what you're going to do is You're going to drop the rock. You're going to time how long it takes for the rock to hit the water. And then we're going to use the constant acceleration equations to figure out the height. Okay. So let's say that it takes 1.2 seconds for the rock to hit the water. How high is the bridge? Make sure there's no boats coming before you do this. Okay, so who remembers the first step that we take on constant acceleration problems? Yep.
And what you want and what you study.
That's the second step. We have to do one thing before that. Yep.
Say the error is negligible.
Yeah, that is important. That's not included in my 4 steps though. So just from this is something I talked about on Thursday, okay, so the first step is the 4 things that you have to choose are, you have to put a sticker, an imaginary sticker where the position is equal to 0. You have to choose what direction you're going to call positive and what you're going to call negative. Remember that? And then you have to turn the stopwatch on at some instant and turn the stopwatch off at some instant. Okay? I am going to do what I pretty much just always do on free fall and projectile motion problems. I'm going to choose my 0 position to be at the lowest point that we're going to have in the problem. So I'm going to call the water 0. And then I'm going to call positive up and negative down. And there's no reason you have to do it like that, but I think it's helpful to always do it the same way, and this is the way I always do it. Probably the way most people always do it. And now we have to choose the 2 instants where we're going to turn the stopwatch on and off. So what's the instant that we're going to turn the stopwatch on?
When it leaves our phone.
Yep, that's right. So at the instant that it's dropped, we're going to start the stopwatch. And what's the instant time final when we turn the stopwatch off?
When it hits the water.
Yep, the instant that it hits the water. And so now we've chosen all 4 of those things. And now we can go to the second step, which is listing out the variables we know and want. So I'm going to list out all of the variables that appear in those equations. So we can just go through them and cross them off as we go. So time final, acceleration, P initial, P final, V initial, and V final. Okay, so time final is what the stopwatch says when we turn it off. Do we know what time final is?
Yes.
Yes, we do. That's one thing we're given. Yep, so 1.2 seconds. Do we know the acceleration? In the kind of problems we were doing before, we're not given the acceleration, we don't know what it is. But in a free fall or projectile motion problem, you know that the acceleration is 9.81 meters per second squared down. Okay, is down our positive or negative direction? Negative, and so the acceleration is negative 9.81 meters per second squared. Okay, now do we know the position when at time equals 0, when the object is dropped? No. Do we want that? Yeah, that's the thing that we're trying to solve for. If we know that, we can answer this problem. Do we know the position when it hits the water? Yeah, we do. That's what we chose as our 0 position. So P final is equal to 0 meters. Do we know the velocity when time is equal to 0?
0?
It is 0, yep. And so remember, this is related to the first of these 2 useful facts. This object is just dropped from the bridge. The bridge, if it's a good bridge, has 0 velocity. That's like a really important trait of a bridge. And so yeah, as soon as you let go of it, the velocity is equal to 0, and then from there it'll speed up. So V initial is 0 meters per second. And then the last one is, do we know the velocity of the rock so think of this, instead of thinking it as the instant when the rock hits the water, think of it as the instant right before it hits the water, or else think of it as the water's gone, it's not there at all, and what would the velocity be when the rock reached the height of the water? Okay, so do we know what that velocity would be? No, but if we can solve the problem without it, that's fine with us. So there we go. And now we have to go through the 3 constant acceleration equations and try to find one that has pi in it and everything else in it is known. So let's just think about them one by one. So here's the first equation. Vf is equal to Vi plus ATF. Does it have pi in it? No, so right away we know we can't use that. How about the second one? The second one says PF is equal to PI plus VITF plus 1/2 ATF squared. Does this one have PI in it? Yes. And now let's go through the other variables. Do we know PF? Yes. Do we know VI?
Yes.
Yes. Do we know TF?
Yes.
Yes. Do we know A?
Yep.
Yep. So this one's going to work.
Can you zoom in a little bit?
Yeah. Sure. So let's just start plugging this stuff in. PF was equal to 0. We're trying to find PI. It doesn't help if I just write smaller after I zoom in. VI is 0. TF is 1.2 seconds. Then plus 1/2 times negative 9.81 times 1.2 squared. 0 times 1.2 goes away. And so we have 0 is equal to PI plus if you multiply all these out, you get negative 7.06. And so now just do the algebra and you get that PI is equal to 7.06 meters. Or about 23 or 24 feet, somewhere around there. Yes?
On the testing exam, will you give us 3 equations?
Yes. Yep, I'll always give you any equations you need, and I'll always give you any conversions you need for the problem. Any other questions about this? So you can see it follows the same steps as every other constant acceleration problem, but you know a couple of other things because it's a free fall problem. Okay, let's ask one more question about this. When we got to V final, we didn't know what the velocity was when the rock reaches the water level. Let's calculate what that is. So what's the velocity of the rock just before it hits the water? We're going to go through the same steps that we did last time. The first one is to choose those four things. Choose what we're going to call position equals 0, what we're going to call the positive direction, what we're going to call time equals 0, and what we're going to call time final. The only times you ever have to change those choices in the middle of a problem is if it asks you something about an instant that wasn't one of your two time choices before. Okay, so in this case, there's no reason to change those four things. And it saves you a bit of time if you keep the four the same. So in this case, we're going to keep the same position equals 0, positive direction, and we're going to turn on and off the stopwatch at the same two instants. Okay. What that means is that when we go to figure out what we know and what we want, everything that we knew before, we still know. Okay? Plus, now we know one more thing because we calculated the initial position. So I'm going to list out again all the stuff we know. Our time final is still 1.2. Our acceleration is still negative 9.81. Our P initial is, what was that, 7.06? Our P final is 0. Our V initial is 0. And we still don't know V final. That's the thing we're trying to find. Okay, well, now we know a lot of variables. And so we have multiple options for finding this V final. So let's check these two equations. I just want to show you that both of these will work. So V final is equal to V initial plus ATF. Okay. It has the thing we're trying to find, VF. And we know VI, A, and TF. So this should work. Okay. The other one that will work is 2 times A times the quantity P final minus P initial is equal to VF squared minus VI squared. It has VF in it, and we know A, PF, PI, and VI. So that one will work too. So you could use either one of these, but always, if you have the choice of using this one, do it. For one thing, it's just the simplest looking equation, but it also doesn't have any squares in it. And those squares are kind of a pain because remember, when you take the square root of a variable, that variable could be plus or minus. So if we solve this second one for VF, we're going to get a plus or a minus VF. And then we have to think a little, take a little extra time to think, should our answer be the positive one or the negative one? It's not too big a problem. In this case, which way would the rock be moving just before it hit the water, in the positive or negative direction? Negative. So we would take the negative and that's fine. But it just saves you a little bit of a headache using the simpler one. Okay, so V final is equal to 0 plus negative 9.81 times 1.2. And so V final is equal to negative 11.77 meters per second, which is somewhere around 25 miles an hour. It'll be going about 25 miles an hour when it hits the water. Any questions about that? Okay, let's do another one. So let's say that a ball is thrown straight up into the air. From an initial height of 3 meters. And with an initial speed of 10 meters per second. And we want to know how high is the ball at its highest point? What's the highest point it reaches before it comes back down? Okay, so this is going to look something like this. The ball is going to be thrown from a height of 3 meters. It's going to go up, reach a highest point, and then come back down. And we want to know what this height is at the highest point. So the first step is to choose the position equals 0, positive direction, and the stopwatch on and off instance. Like I said, I just always choose the lowest point in the problem as my position equals 0. So this is where I'm going to say, so I'm going to call this the 0 position. And then I always choose my positive to be up and my negative to be down. And now, what do we want to choose as the instant when we turn the stopwatch on and the instant when we turn it off? So when are we going to turn it on?
When it reads our hand of 3 meters.
That's right. Yep. So our time equals 0 instant. Oh, computer crashed. Our time equals 0 instant is going to be the instant that it's thrown or launched or whatever. And now, what's the instant when we're going to turn the stopwatch off? So what you need to think about is we choose these instants. We choose to turn the stopwatch on and off at instants where we have information and where we want information. Okay, we want information at a very specific instant when it reaches the highest point. And so whenever that's the case, that has to be one of our choices. Okay, so we're going to turn the stopwatch off at the instant that the ball reaches the highest point. Okay, one of the two helpful facts that I gave you, so remember the two facts that we're going to use a lot that I gave you. The first one was whatever you drop a thing from, that the velocity of that thing is the initial velocity of the object. The second one was when an object reaches the highest point in its flight, the velocity is equal to 0. And so whenever you have a problem that deals with the highest point of a flight, you're going to use the fact that the velocity is 0 at that point. Okay, so like, here's how you should read a problem like this. You should see that it mentions the highest point, and you should just be giddy with the excitement of getting to write that the velocity is 0 at that instant in your list of what you know and what you want. You know it's coming. There's no way that it's not coming. Okay. So I'm just going to go through the list of variables. Do we know the amount of time that it takes? Do we know what the stopwatch says when the ball gets to its highest point? No. We don't care though. If we don't need it, that's fine. So I'm just going to leave it off. Do we know the acceleration? Yeah, in free fall, we always know the acceleration. So acceleration is negative 9.81 meters per second squared. If I had chosen my positive direction to be down, what would the acceleration be? Yeah, perfect. Positive 9.81 meters per second squared. Since I always tend to choose my positive up, my acceleration is always negative in free fall. Okay, do we know the initial position? Yeah, so if you start at 0 and go 3 meters in the positive direction, the position is positive 3 meters. So PI is positive 3.0 meters. Do we know the final position? Do we want it? That's what we're looking for. So I'll put that over here as the variable we want. Do we know the starting velocity? It says that at the instant that it's thrown, it has a speed of 10 meters per second. And so all we have to do is think, is it moving in the positive or negative direction at that time? Positive. So the initial velocity is positive 10 meters per second. And then the last one, this is the moment we've been waiting for right here. Do we know the velocity when we turn the stopwatch off? 0, yep, because it's at the highest point. Okay, is there an equation that has PF in it and everything else in it is known? Well, since there's no time final, the only one that could possibly work is the last of those 3 that doesn't have T final in it. So let's check that and make sure that it works. Hopefully it will. So that says 2 times A times the quantity PF minus PI is equal to VF squared minus VI squared. It does have PF in it. A is known, PI is known, VF is known, and VI is known. So this one will work. So I'll start plugging this in. 2 times negative 9.81 times the quantity PF minus 3 is equal to 0 squared minus 10 squared. I'm going to start by multiplying the 2 and the negative 9.81, so that gives negative 19.62 times the quantity PF minus 3 is equal to negative 100. Now I'm going to divide both sides by negative 19.62, and you get PF minus 3 is equal to positive 5.08. And so PF is equal to 8.08 meters. Any questions about that? Yeah.
That's at the top.
Yeah, that's at the top. Yep. So this distance that I put the question mark next to is 8.08. So what is that, like, yeah, 25-ish feet or something, if you want to picture it. And it starts at about 9 feet, a little over 9 feet. Okay, let's ask one more question about this. What's the speed of the ball when it falls back to a height of 3 meters? So it's launched from 3 meters, it goes up to 8 meters, and then on the way back down, what's its speed when it passes 3 meters again? Does anyone happen to know the answer to this? Okay. Yeah.
Would it not always accelerate back to the same speed?
Yes, you're exactly right. So there's a symmetry to these problems. So at any height on the way up and the way back down at the same height, the speed is going to be the same. The velocity is just going to be opposite directions. So the answer that we're expecting, that I'm expecting to get, is negative 10 meters per second. Well, for the velocity, and then the speed would be 10. But let's just go through the calculation. So the first step of this calculation is making those 4 choices. Is there any reason that we have to choose a different time equals 0 or time final? Sometimes there's not, but in this case, yes, because we're trying to find a variable value at a specific instant, and that specific instant is not one of the ones we chose before. Okay, so we're going to have to choose a different time final. Okay. So this time we need our time final to be when it passes a height of 3 meters on the way back down. Okay, so I'm gonna just we're gonna walk through these steps together. So the next step after we choose that time final instant is to list out the variables we know and the variables we want. So here's a list of all of them. Take a few minutes and see if you can fill out this list of what we know and what we're trying to find. Okay, feel free to talk to each other and talk to me and whatever, but see if you can get through this and then I'll go through it. Yes, thank you. And then VF is what we're looking for. All right, so now take a couple minutes and see if you can find an equation that'll let you solve for VF and go through and try to calculate that, okay? And then I'll do it. Okay, so the equation that works here is 2A times the quantity P final minus P initial is equal to VF squared minus VI squared. So plug this stuff in, you get 2 times negative 9.81 times the quantity 3 minus 3 is equal to VF squared minus VI squared. 3 minus 3 is 0, so everything on this side goes away. And so you get that VF squared is equal to VI squared. Take the square root of both sides and you get that VF is equal to plus or minus VI. And now you have to think, which one am I interested in here? So the initial velocity when it was launched up was positive, but now it's on the way down, which is negative. And so VF is negative 10 meters per second. Any questions about that? Okay, so why does this work? You don't have to this isn't going to be on tests or anything like that, but I just wanted to show you for a problem like this, if you draw a position versus time graph, constant acceleration, position versus time graphs are always parabolas. So this would look something like this. Okay. And so at any height, you can choose any height you want where you can catch it on the way up and on the way down. And the velocity on the way up is the slope of that. The velocity on the way down is the slope of that. And so you can see because of the symmetry of this parabola, on the right side of every one of those heights, the slope is the opposite of on the left side of one of those heights. Okay, so no matter what height you're talking about, the speed going up at that height is equal to the speed going down, which is why cities don't want you to shoot guns into the air on 4th of July or whatever, I mean, if there was no air resistance, a bullet, when it got back down to the ground, would be exactly the same speed as it was shot at, which is a very high speed. That's not really true because there's a ton of air resistance on bullets, but it's still going to be going very, very fast. Definitely enough to kill people and things, Okay, anybody have any last minute questions about that example? Yeah.
To go up a little bit further. Thank you. When I actually broke down for the VI squared,
Mhm.
and I did the solving it.
Yeah.
I did get a different answer. Like I got 8.9 something.
Did you have everything right up to this equation?
Yes.
Okay.
I did, but for the VI, I actually put in 10 meters per second, and I could then solve it. Yes. like I tried to,
Mhm.
I don't know what the English word is, I don't know, but
Square root, yeah.
square root. And like I got a different answer, I got 8.9 something.
Huh. Yeah, you just punched it in wrong somehow. We could talk about it after class. I'm not sure what happened, but I mean, I'll show you how you would punch it in. Any other questions? Okay, let's stop there. See you on Thursday.